Negative feedback amplifiers. The first thing is open loop amplifier. That we call it as basic amplifier. Basic. For example, take an amplifier like this. This is output voltage, input voltage. This is amplifier A. There is a supply. In this amplifier, you have active device. Active device. Therefore, what are the drawbacks of basic amplifier? The first drawback is drift in supply. Second, drift in device parameters. Drift in supply, drift in device parameters. When you say drift in device, these two together makes gain unstable. Unstable gain. Then third one is distortions. Fourth one is noise. Fifth one is RI is not high. R0 is not low. Because when you say voltage amplifier, RI should be high, R0 should be low, gain should be high. So when we want high impedance, it's not high. When we want low output impedance, it's not low. That's why these are the drawbacks. And what is the remedy for this? The remedy is negative feedback amplifier. That's a purpose. The purpose is to see that all these problems are satisfied. In fact, you have one more problem. Bandwidth is less. In fact, bandwidth should be higher. How to solve them? One good news is all problems are solved with one single remedy. Not that some of them are by here, all are by that. So let us go to the second point, block diagram of negative feedback amplifier. Take this as A, V0 or X0 call it. Then you say XS, beta here, plus minus XI. XI. So X0 by Xi is equal to A. So X0 is AXI. XF we call it, XF by X0 is beta. Output by input, this is input. Therefore, XF is beta into X0, that is A beta Xi. If you substitute X0 here, then AF is X0 by XS. What is Xi here? Xi is XS minus XF. Therefore, Xi plus XF. This is AXI, Xi plus A beta Xi. So it is called A by 1 plus beta. That's the gain that we are going to get. By this you understand one important thing without further discussion. Gain is decreased. So feedback could solve all the problems, but the gain is decreased. So now my rest of the time that I'm going to talk is how all these problems are satisfied. So let me tell you how these problems, all the 7 problems are solved one by one. Third point, types of basic amplifier or open loop. How many types are there? There are 4 types. First one, voltage amplifier. V0 is proportional to Vi. AV into Vi. Take for example like this. This is Ri R0. Output should be voltage. Input should be voltage. When both are voltages, we call it as, what do we call? We call it as voltage amplifier. When this is voltage, we have to give voltage source. And when you give voltage source, the resistance become serial. Then this should also be voltage, AV into Vi. Because this is voltage. And because it is voltage, it should be in series. Because this voltage, it should be in series. Once again, when this is voltage, this should be voltage, therefore series. When this is voltage, this should be voltage, therefore series. Connect them. Now this is actually inside. This is called amplifier. But the question is, what are the characteristics? What are the behavior? For example, the question is how to maximize V0. Because the very purpose of an amplifier is maximizing output. This being a voltage amplifier, output is voltage. Therefore, Vi should be approximately Vs. If you want to maximize this, you should maximize this. This should be maximum means this should be negligible. This should be maximum means this should be negligible. Therefore, Rs is far less than Ri. V0 to be AVVI, R0 to be far less than load. For you want maximum here, this should be negligible. For this to be maximum, this should be neglected. Therefore, Ri should be high, R0 should be low, gain should be high. These are the very important characteristics of an amplifier. These 3 are serious. But very unfortunately, if you take BJT, in BJT input impedance is low. In BJT input impedance is high. Output impedance is high. When I'm asking for 0, it is giving high. When I'm asking for high, it's giving low because input is forward bias, output is reverse bias. So we is unable to achieve what we wanted. But how to achieve that? For example, look at this small table I am trying to help you. Ri, R0, gain. BJT, FAT, op-amp. You know what happens? In BJT, this is low, this is high. Gain is medium. This is high, this is low, gain is low. High, low, high. That's the meaning. Now what does it mean? Will you please look at this? In terms of resistance, this is bad, gain is okay. Impedances are good, gain is bad, but both are good. That's why we need operation amplifier. When the individual circuits are unable to do, we need integrated circuit. So BJT is good in gain but not impedances. FET is good in impedances but not in gain. But op-amp is good in all. That's the voltage amplifier. So that's the first amplifier called voltage amplifier. So how to achieve these things that we wanted? What we wanted infinity, but what is there? How to achieve these impedances? These impedances are achieved by negative feedback. That's why we need feedback amplifiers. Second one is current amplifier. Current. What do you mean by current amplifier? Look at this. RI, II. RL, I0. RS, IS. We have a dependent source here. II. So this is amplifier. Now what are the achievements you have? II should be approximately IS. I0 should be approximately AI into II. Like that. If II has to come here, this should be larger. RS should be far greater than RI. If this has to come here, R0 should be far less than RL. R0 should be far high. Why? If this is high, that goes there. If this is high, that goes here. Current seeks for less resistance path. Therefore, what is our conclusion? 3 conclusions. RI should be low, R0 should be high, current gain should be high. These are the expectations of current amplifier. So I will give you a small table, parameter X0, XS XI, gain X0 by XI, RI, R0. Voltage amplifier, current amplifier, trans resistance, and finally transconductance. These are the 4 amplifiers. This is V0 VI, I0 II, V0 II, because voltage by resistance, current by resistance. So this will be AV, V0 by VI, AI, I0 by II, RM, V0 by VI, II, GM, I0 by VI. RI is infinity and 0, 0 and infinity. Here, how do you know other 2? Other 2 are combination of these 2. When input is current, when output is voltage, output impedance is 0. When input is current, input resistance is 0. When output is current, output resistance is infinity. When input is voltage, input resistance is infinity. So, basing on the first two, I can make others. So totally we have 4 amplifiers: voltage amplifier, current amplifier, trans resistance, trans conductance. This is called basic amplifiers. This is our first amplifier, second of this, third and fourth is a combination of other two. So this is basic meaning of basic amplifiers. Third point. Negative feedback amplifiers topology. Topology means arrangement. Look at this basic thought. This is A, X naught, Xi, beta, XS, XF. So what is Xi? Xs minus Xf. There are two possibilities. What are the two possibilities? If it is voltage, Vs minus Vf. If it is current, Is minus If. This is mixing currents, mixing voltages. This is mixing currents. When voltages are mixing, voltages means subtracted means series. When current is added or subtracted means shunt. So shunt mixing, series mixing. Then similarly, when it comes to I naught, we have two things, V naught, I naught. This is called voltage sample. This is called current sample. So as for sample means taking something. You are taking a voltage sample, current sample. So voltage series, voltage shunt. Current series, current shunt. Like that, 4 topologies got achieved. Like that, I am going to make one topology now. The first topology is, let me try with you. You follow me. This is a voltage amplifier. Input is Vi, output is V naught. Same voltage should come here, like this. This is V naught because this is V naught, but this is Vi not because of Vf. Vi means it should be Vf. These two should be same, these two should be same. Follow that. When this is voltage, voltage will come when you take parallelly. Parallel voltage will be same. Then voltage and voltage, take a voltage source and voltages are mixed serially. Apply KVL, Vs minus plus Vs minus Vi minus Vf 0. Vi is Vs minus Vf, that is series. When voltages are subtracted, it is series. That's why this is called voltage series feedback. Voltage series feedback. That's the meaning. Now, what are the things we are going to have? First point is D, D-sensitive factor. Second point is AVF, AV by D. Third point is RIF, R0F, bandwidth. Everything is with feedback. What is RIF here? When we say series, RIF is multiplied. When you say shunt mixing, RIF is divided. When you say voltage sample, R0F is divided. When you say current sample, R0 is multiplied. Once again, series means multiplied, shunt means divided. Voltage means divided, current means less. This you have to follow now. Now you tell me, input is series, that's why this should be divided. Output is voltage, that's why this should be multiplied here, divided here. Bandwidth is multiplied. When the gain is decreased, bandwidth is multiplied. So everything depends on this D. The D is called desensitivity factor. Desensitivity factor. Why it is called desensitivity? It is desensitizing the variations, the changes, that means stabilizing the gain. Now cross-check your concept. Please go to my table I gave just in the last test earlier. When a voltage amplifier, impedance should be more, it is multiplied, more. Output impedance should be less, divided, satisfied. Bandwidth should be more, satisfied. The only drawback is gain is decreased. You are able to get everything, but with a drawback of decreased gain. No problem. More gain unstable is not good. Less gain stable is good. That's called voltage series feedback. Let us go to second topology. Second means I'll give you amplifier, you think of arrangement. How does it do? It's a current amplifier, gain is AI. This will be a current, this will be a current. Both are currents. This current is, same current should come here. When? Serial. If this is current, this should also be current. If these are currents, I should take current source. If I take a current source, that will come like this. So this is IS, this is IF. Apply KCL. Entering is minus, leaving is plus, leaving is plus. So IF is IS minus II. IS minus II. That's okay. Or II is IS minus IF. By this you can say, what mixing is that? Current mixing. Current means shunt mixing. Shunt, output is current. So this is called current shunt. Current shunt. Understand, only possible topology with current amplifier is current shunt. What are the changes coming? D is 1 plus AI beta. AIF is AI by D. R0F RIF, bandwidth with feedback. When gain is decreased, bandwidth increase. That's not a great thing to talk. But impedances, you tell me, shunt means what? Divided. Current means multiplied. In a current amplifier, input should be less, output should be high. Both are satisfied. Bandwidth should be high. Only drawback is gain is decreased, but stability achieved. So let me summarize. Parameter. voltage series, current shunt, current series, voltage shunt. Voltage series, current shunt, current series, voltage shunt. X0, XS, XI, XF. AX0 by XI, beta XF by X0. D is 1 plus A beta. RIF, R0F, bandwidth F. This is the summary. What is X0? What is the voltage series means? Output is voltage, input also voltage. V0 by Vi, Vf by V0, AV beta, Ri into D, R0 by D. This is same. Output is current, input is current. Current amplifier, IF by I0, AI beta, Ri by D, R0 into D. So voltage series, current series. Current series means output is current, voltage, voltage by current, current by voltage, 1 plus Rm beta, voltage by current, Gm, voltage shunt, output is voltage. So this is current by voltage, Gm, this is Rm, 1 plus Rm beta, this is Gm beta. Beta is here XF, IF by V0. Here beta is Vf by V0. So this is 1 plus Gm, this is 1 plus Rm. You tell me, both decreased, resistance means both decreased. Input is current, output is, here both increased. So you could achieve all the parameters that is required in this. Therefore, what are the achievements? Impedances are achieved, bandwidth is achieved, same, multiplied. All advantages came. Therefore, advantages of negative feedback. First one, gain is stabilized. How is gain stabilized? Suppose AF is A by 1 plus A beta. If A beta is far greater than 1, AF is 1 by beta. If AF is far greater than 1, A beta far greater than 1 is neglected. Therefore, stable. That is one way to look at. Second way is AF is A by 1 plus A beta. DAF by this, you will get 1 plus A beta whole square. DAF by DA, 1 by 1 plus A beta, A by 1 plus A beta, then multiply, divide. So DAF by, if you bring AF here, this is nothing but AF, is equal to 1 by 1 plus A beta into dA by A. What happened? This is without feedback. This is with feedback. With feedback became smaller because by. So therefore, DAF by AF is far less than dA by A. That's the first thing. Gain is stabilized. Second point, Ri is R0. Both are as per requirements. I can't say increase or decrease because in some cases it is should be increased and increased. Some cases it should be decreased. Then when gain increase, there is a lot of noise. But now feedback gain is decreased, so noise effect also decreased. Then bandwidth is, when gain is decreased, bandwidth automatically increases. Therefore, all advantages at the cost of AF decreased. All advantages at the cost of decreased gain. So the only drawback is gain is decreased. All advantages came. So gain is decreased but stable. In order to achieve the requirements, we need to go for feedback. This is called analysis feedback amplifiers. Analysis of negative feedback amplifiers. So far we have seen concept, we will see now analysis. Step 1. Identify topology. Identify topology. How do you know that? Input, output. If input is directly given to base or gate or signal point, then it is shunt mixing. Shunt mixing. If output is voltage, if output is V0, that is voltage. If output is I0, current. Now what is the topology? If output is current and input is shunt, current shunt, voltage shunt. If it is not given to base or gate or signal point, it is not shunt. Otherwise, if not shunt, it is series. Here, if output is directly taken from V0, then it is voltage sample. Otherwise what? Current sample. Therefore you have two options. Voltage sample, otherwise current sample. Shunt mixing, otherwise series mixing. Using this concept, you can identify one of the four topologies that you have. I already told you that there are four topologies here. Beta is xf by x naught. Calculate that. Third one is basic amplifier. How do you draw basic amplifier? For input circuit, go to output, put x naught 0. For output circuit, go to input, there are two ways for input. If input is current, open it. If input is voltage, short it. By doing these things, you can draw basic amplifier. That is third step. Fourth one, calculate A, Ri, R naught. Of what? Of basic amplifier. Fifth one, calculate AF, RIF, R naught F. So this is called 5-point procedure of analyzing any amplifier. There are several amplifiers, For example, there are 4 topologies: single stage, multi-stage. Total you can have 8. So we will see some problems and see how we analyze and use this procedure I have given. I said this is base because of BJT, gate is FET and signal point is op-amp. So most of the objective questions in competitive exam, they are saying this point itself is a main thing for them, identification of topology. Because asking all the 5 steps is a very difficult job, is a time consuming job, you can't do that. Maybe in only IES they can ask you this, but otherwise in objective questions like gate, any public sector unit, they don't ask all the 5 steps, but they'll ask mainly first step or some other steps. So let us see that. Problem 1. Calculate AVF, RIF, R naught F. Look at this problem. Like that. This is V naught. Vs. Okay. How do I explain these 5 steps here? Solution. As you know, first one is basic amplifier or feedback topology with basic. What topology is this? What is feedback actually? Anything common for output to input is called feedback. So there is something called output to input, that's called feedback. Output is taken directly from voltage, so it is voltage sample. Output is directly given to base, therefore it is shunt mixing. So voltage sample here, shunt mixing is here. If you combine these two, this is called voltage shunt. Voltage shunt. Secondly, calculate beta. Beta is xf by x naught. What do you mean by voltage shunt? Output is what? Input is what? What is gain? Voltage means output is voltage. Shunt means mixing current. Therefore, this is RM. So, it is trans resistance. If XI, XF, XS all are same. So, this is current means II by V naught. What is II here? IF. What is IF? This is IF. This is IS. II. IF is V naught minus Vi minus V naught by V naught. Vi is very small by RF. Once again, IF is Vi minus V naught by RF by V naught, neglected. This is minus 1 by RF. That's called beta value. Step 3. Step 3 is basic amplifier. What did I say there? Output is V naught. What did I say? Short it. Put X naught 0, means voltage. Input is shunt. Shunt means ground it, I said. So make this 0, input will come. Make this 0, that means RF. Make this 0 mean RF. This is RF. And remaining you draw RL or RC. Like that. This you combine, or this you say Ri dash, Ri, R naught dash, R naught. Ri dash is HIE, Ri is RF parallel HIE. Why? The parallel combination of these two is Ri. These two are in parallel. R naught dash is infinity. R naught is infinity parallel RL is RL. What is RL? RC parallel RF. That is actually step 4. What is step 4? Analysis. Then what is current gain? HFE. Current gain is HFE. Then what is RM? RM is V naught by II, I naught II into RL. That is nothing but current gain into load minus HFE into load. That is RM. Lastly, step 5. What is step 5? D is 1 plus Rm beta. RMF is V naught by Is Rm by D. Therefore, AVF is V naught by Vs, V naught by Is into Rs, RMF by Rs. RIF, R naught F. What is RIF? In a trans-resistance amplifier, both are by D. Whatever that you got here by D, whatever you got here by D. And from the current gain we have developed. So you can get from RMF you can get AVF. From AV you can get RI. So this is all about analysis, how you can analyze all the 5-step procedure for this problem. Problem 2. Identify topology. This, for example. RSVS, RCRE. If we take here, what is it? Output is directly taken from V0, so voltage sample. Feedback is not given to base. That means not shunt. It's not going to base, not shunt. If it is not shunt, what is it? Series. Therefore, voltage sample with series, this is voltage series. Like that, one has to identify which topology it is that. Problem 3. Same problem, but slightly different. Instead of taking here, we take from here. We take there. So this is taken from voltage. What is the difference between these two? Here, feedback is here. The sample is not voltage. Because voltage is here, it is not taken. So not voltage means what? Current. Not given to base, series, not shunt, therefore series. So this is not voltage series, this is current series. Here, output is directly taken from voltage, so voltage sample, not given to base, so not shunt, therefore series. So overall it is voltage series. So please remember, I am concluding very interesting things. CE without, this is common emitter. CE without feedback, CE with feedback, this is called CC. And our first problem is CA with collector to base. So CE without feedback is no feedback or basic amplifier. CE with feedback is this, that is called current series. CC is voltage series, and CE with collector to base, what did I say earlier? Voltage shunt. These are the three conclusions we have. By that you can identify the topology. So identification of topology, and there are very serious objective questions. Common emitter without feedback, common collector to base, bias. These are the different names we have. Problem 4. Let us look at op-amps. R1, R2, VI. What is this? This is a feedback. Is it given to signal point? No. So output is taken. So output is taken from voltage. This is not. So output from voltage. So voltage sample. Input is not given to base. So not shunt. Not shunt means what? Series. So this is voltage series. What is voltage series feedback? Non-inverting topology. So non-inverting amplifier is an example of voltage series. Problem 5. R1, R2. This is a feedback. X0 is directly taken from voltage sample. And input is directly given to signal point. When it is directly given to signal point, we say shunt mixing. Therefore, this is voltage shunt. What is voltage shunt? This is inverting. So inverting amplifier is voltage shunt, non-inverting is voltage series. Non-inverting is voltage series, inverting is voltage shunt. These are the things that we have. Problem 6. RC1, RC2. This is direct. And here you have a resistor. R1, R2. What feedback is this? Directly taken from voltage. So voltage shunt. Voltage. The second end is not going to base. Not shunt. Not shunt means series. Therefore, it is voltage series. But this is cascaded. What do you achieve from cascading? You get more gain, and more stable. Cascading will give more gain, feedback will give more stability. Problem 7. What about this? Say this is R1, R2. Output is here. What is X0? Not voltage. Because voltage here, but you're taking from here. Not voltage means what? Current. What is input? Given to base. Base means shunt. Therefore, current shunt feedback. That is current shunt. Like this topology we have to know. Once you know topology, you can do anything. Problem 8. This is a linked problem. Calculate beta if 1% of AF with A is 1000 plus or minus 100. Problem 9. Calculate AF. That's called linked problem. Why it is linked? We get beta from here, that beta we use here, that's why it is called linked problem. Solution. DAF by AF is equal to 1 by 1 plus A beta dA by A. He said 1%, that means 1 by 100, this is 1000 beta, 100 by 1000. Solve for beta. That is problem 8. After getting beta, AF is A by 1 plus A beta. 1000 by 1 plus 1000. Whatever beta that comes from here, you substitute, you'll get AF. That's why it is called linked problem. Last problem, problem number 10. A is 1000 plus or minus 100. Input is 10 milli. Loss of gain is 40 dB. Calculate V0. Then AF. What's the meaning of this? Look at this. A is 1000. VI is 10 milli. Therefore, V0 by VI is AV. Therefore, V0 is A into VI. How much? 1000 into 10 milli. Milli and 1000 cancel, so output is 10 volts. That's one answer for my question. Second answer is AF is A by 1 plus A beta. Take 20 log minus 20 log A is minus 20 log 1 plus A beta. What I mean is, this comes here, so negative, this is 1 by negative. This is called loss of gain. Why it is called loss of gain? Because A is greater than this, so negative. Now what he says, for example, if this is x minus x, so minus x is minus 20 log 1 plus A beta. So 1 plus A beta is 10 power x by 20. Minus minus cancel, x by 20, log base 10, so it comes over here. So when they speak in terms of loss of gain, you must understand this, and in our example, it is given as 40, therefore it is 100. X is 40, he said, 40 by 20 is 2, 10 power 22 is 100. Therefore AF, what is it? 1 by 1 plus A beta, 1000 by 1 plus A beta is 100, AF is 10. So you can drastically understand gain is decreased from 1000 to 10 but stable. Similarly here also gain is decreased from 1000 to this. So that's why I've been telling gain is decreased but there is a stability. That's the end of negative feedback amplifiers.